T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0. And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Hi all. Today we're rebroadcasting Aaron's interview with David O., who was, among many other things, the flight director for the Mars Curiosity rover, which you're hearing in the background there. O is the current systems engineering manager and system architect at NASA's Jet Propulsion Laboratory for the upcoming Psyche launch.
NSL is now breaking the sound barrier.
When I asked Aaron why he chose this episode, of all our past episodes, as one of his most favorite, he said this. David was in the control room at 2 a.m. and was one of the handful of human beings to learn something about our neighboring planets that no one had ever learned before. Plus, it's NASA, and NASA is just so cool whether you're an engineer or not. So join us as we revisit David O's guest appearance with Aaron on this week's Being an Engineer.
There is nothing like being in the control room when the rover's on the surface and looking at pictures at 2 or 3 o'clock in the morning as they come down and thinking, we are the first human beings ever to have seen what we're looking at right now.
Hello and welcome to another episode of the Being an Engineer podcast. Our guest today is David O., who, in my opinion, will end up being one of the more fascinating guests that we have had on the show to date. David holds an undergraduate degree from MIT in aerospace engineering, as well as master's and doctorate degrees also from MIT in aerospace engineering. He has been working at NASA's Jet Propulsion Laboratory for over 17 years, where he previously held the role of flight director for the Mars Curiosity rover and is currently the systems engineering manager and system architect for NASA's Psyche program, which we'll get into during the show. David, thank you so much for being with us today.
Thank you, Aaron. Good morning. You didn't mention that I have a bachelor's degree in music, too. So
I'm getting there. I definitely have a question about that one. In fact, why don't we just start there? So you actually double majored, I guess, at MIT. One was humanities and music, and the other one was aerospace engineering. I have to know more about that. Tell me about the humanities and music major.
Well, I was a musician. I was a singer and a piano player in high school. And when I got to college, I wanted to continue doing that. And MIT actually has an excellent music program. It's an engineering school, but it has a small but excellent music program. So I
had no idea.
Couldn't turn down the opportunity to go study there and get my degree. And that was a wonderful thing to do.
And you thought to yourself, I'm going to major in aerospace engineering and become a rocket scientist. With all the free time I have, why don't I just double major in humanities and music?
Yes, that's right. Actually, I mean, I find the jumping between disciplines, jumping between music and engineering, I found it then and I find it now to be very gratifying. I'm not the kind of person that can just do 100 hours a week of just engineering. I need a little break to go do other things as I go.
I think there's a link there. Several of the team members at Pipeline actually are musicians as well. One of them writes his own pieces and publishes them. One of them has been in a band for many years, and actually two of them have been in bands, and they play the fiddle and all kinds of different things, guitar. So I think there is some kind of link between music and the very technical nature of engineering that is, I don't know, it works well together somehow.
Absolutely. And I know multiple people at JPL who played in bands, then went back to go do engineering. I think one of the chief engineers on the Perseverance rover used to be in a rock band and then decided to go study engineering. So it's very common, I think, remarkably common to have that overlap.
Yeah, very cool. Well, were you a Legos kid growing up? Were you always into building things and taking things apart?
I did do a lot of Legos growing up, and I did some woodworking too. I did the kind of stuff, take the shop class at school, that kind of thing. Building things was always fun.
Did you know from a young age that you wanted to work at NASA or be in the aerospace field, or was that something that you became aware of just in college or later?
Well, that's an interesting question because I grew up in Alabama and I liked space and I liked aerospace. Went to the Space and Rocket Center in Huntsville all the time when I was a kid, even though I lived in Birmingham, which is an hour and a half away. But to be honest, because my parents are doctors and not engineers, and there's not much engineering in Alabama, in Birmingham at least, where I lived, I didn't really know what engineering was when I went to college. I just kind of knew I was good at science and math, and knew that I wanted to go and maybe be a physicist or something like that. I didn't really learn what engineering was until I got to college itself and started asking around and said, "Oh, this looks like something that would be fun to do."
And what did you hear about engineering that clicked in your brain and told you, "Yep, this is the one for me"?
That's well, I think one of the things is I went and I thought initially I might be a physicist, and I took some of those freshman physics classes, and I just decided that really wasn't what I wanted to major in. Very theoretical, right? A lot of equations and thinking and not so much building. And then I remember when I got to the lab and got to the university and just started asking around. I remember asking somebody, what do mechanical engineers do? And the answer to that is pretty much everything, right?
Everything.
And I honestly didn't know that because I knew kind of what computer scientists did, but the concept of mechanical engineer versus aerospace engineer versus other engineering was just something that didn't really know about. And then in the course of my freshman year, before I had to choose, I was asking around and thought maybe I'll do architecture, maybe I'll do aerospace, maybe I'll do mechanical, and I ended up just deciding when I declared my major, I'll try aerospace and see how it works out. And fortunately for me, it's worked out well, and I've gotten to work in it ever since.
Never looked back after that.
That's right. It's a fun area to work in, and space is something that I've always been interested in since I was a kid. Like so many people in my generation, the Challenger disaster was something that happened when I was in high school. I remember where I was when it happened, as do so many other my friends and colleagues. And so these events, I was born in 1969, which is when we landed on the moon. So I am a child of the space age.
Oh, wow.
And so it's always been Star Wars, Star Trek has always been fun. And then just the idea that I could actually go build and work in that area has been a dream for me. And so that's just fun. But it wasn't like I sat down at the beginning and said, yes, I want to go be an aerospace engineer. I just kind of said, well, I think space is cool and engineering is cool. Let's see if we can make this work. And I've been fortunate and blessed that it has.
Well, space and engineering are cool. And speaking of space, you work in the Jet Propulsion Laboratory at NASA, JPL for short. Can you tell us a little bit about JPL? I mean, what do the teams do there? What's kind of the overarching mission? What's the reason that JPL exists?
So JPL is one of NASA's 10 NASA centers. Uniquely among the NASA centers, it's what we call an FFRDC, a federally funded research and development center. So it's technically run by Caltech. I technically run for Caltech. And then Caltech runs the facility for NASA. And all of us there work on a variety of missions for NASA. But JPL is one of NASA's premier deep space centers. It is built and operated the Voyager missions that went to Jupiter and Saturn and Uranus and Neptune, the Galileo mission that went to Jupiter after that. It's built missions that have gone to most of the planets. So it's one of the few places in the world, actually, that has the ability from the beginning to end to do a deep space mission. We have the scientists that come up with the ideas. We have the operations centers and the deep space network, and we have everything in between, the manufacturing and the mechanical and electrical manufacturing and the computer coders, so we can build a spacecraft from scratch and send it to another planet. And that's almost, I don't think it's quite unique, but there are not many places in the world that can do it.
Wow, listening to you talk about that, I get chills, I mean, if you can say it this way, that sounds like NASA. That's kind of the core at NASA. It would be funny to hear, do people who work at JPL, do you guys kind of, walk around with a little bit of chip on your shoulders that, we're kind of a big deal here at NASA? Or do you guys, are all the other centers there kind of the same in terms of, I don't want to say priority, but maybe you know what I mean?
I do. And, I I want to say that, first of all, JPL does a lot of stuff in robotic space flight, but we really don't do very much in human space flight. So the space shuttle, landing on the moon, that type of stuff, that's also NASA, and that's kind of the big NASA that people know. Now, when the space shuttle stopped flying for a while, we became much more prominent because we're doing the Mars landings. We're landing rovers. We landed the Mars exploration rovers in 2003. We landed the Curiosity rover in 2012. That got a lot of publicity just because of where NASA was and what it was doing at the time. But with the return of human spaceflight coming, with the new commercial crew and the continued operation of the space station, I think that NASA will have a great future working in human spaceflight as well.
Yeah, thank you for clarifying that. That makes a lot of sense now. Speaking of the Mars Curiosity mission, back in 2012, you were the flight director for that mission. And I definitely want to get into that a little bit before we go straight into the technical side of it. I read that you and your family had a really interesting experience living on Mars time for several weeks. Can you tell us a little bit about that experience?
Sure, I can do that. So I worked on the Curiosity rover for 7 years, and the last couple of years of that I spent doing mission operations, but I actually worked a whole bunch of years before that on building it. So the very end of that process, but part of my career, was when we landed on Mars. We started operating the spacecraft on Mars, and the rover, when it operates on Mars, operates on Martian time, actually. It wakes up in the morning, it gets orders from Earth, it goes and does its thing on the surface of the planet, whatever it's going to do, takes its pictures, does its drilling, and then at night it goes to sleep. The rover doesn't have headlights on it or anything like that, so at night it's dark, and it recharges its batteries off of its nuclear power source, and then it wakes up in the morning and goes through that cycle again and again. Now, a Martian day is the natural operating cadence of the rover, and a Martian day is 24 hours and 40 minutes, so it's 40 minutes longer than an Earth day. For the first 100 Martian days that we operate on the planet, and a Martian day is called a sol, so for the first 100 sols we operate on the planet, we actually sync up the operations teams on Earth to operate at the same time at the rover. So the operation team wakes up at the same time as the rover, goes to sleep at the rover, actually what we do is we wake up when the rover goes to sleep. So we're doing work at night, and then we send orders to the rover, and it does its thing while we sleep, and then we continue that cycle over and over again. So we're operating on this rotating shift system where we come into work about 40 minutes later every day. And if you do the math, you'll find that that's the equivalent of jumping 2 time zones every 3 days. And over the course of a month, you basically go all the way around the clock. You all go all the way through swing shift and night shift and come back around to day shift. And that's kind of a unique thing that we do for the Mars program. And the brilliant idea that my wife had with this, because we landed in August and the kids weren't in school, was let's just take the whole family and put it on Mars time as well. So we put the whole family, including the 3 kids that we had, on Mars time. I think the oldest one was 13 at the time, and the youngest was like 7. Those are approximate ages. Don't quote me on that. And then so they got to follow around the clock with us as well. And that was a great time because we would take them to go see LA at night, right? We would be having dinner at 2:00 in the morning at Denny's or at IHOP or some all-night diner in Hollywood. We took them out to see Hollywood at night. We took them out to Santa Monica and did a midnight on the beach, a picnic on the beach at midnight. And it was great fun. And it was really just a great time for the whole family.
They must have loved that. I think of my kids, and if they had that experience, they would find it just so cool, right? I mean, were your kids telling their friends, sorry, we can't come out to play tomorrow because we're on Martian time and we're going to be asleep during that time? Were they really into that?
Yeah, they were young enough that they kind of just went along with it at first. I don't think they realized how unique an experience it is. But
okay.
We are the only family that I know of where the whole family has gone off and done it. Yeah. And at the end of the day, I think they loved it. My oldest son, he was 13. It was it's a very important time in his life when he's forming ideas, and he's going off to major in engineering now. And I think that's part of his whole experience that led to that. And they had no idea that, you can go bowling at 2:00 in the morning, at 3:00 in the morning. They had no idea of the breadth that is Los Angeles, because it's a 24-hour city and all the great things you can do. Yeah, I think they loved it.
What a magical experience. How did that time shift, especially not just being on a different schedule, but on a schedule that changed by 40 minutes every day, how did that mess with your and your team's biology and physiology. Was it easy to cope with that, or was that a really big challenge?
It's both in a funny sort of way. An extra 40 minutes a day is not that hard if you're consistent with it, and if the rest of the world goes with you, which it doesn't. So when the whole family was doing it, I actually found it to be very natural. And we got to a point with the family where we would just go to sleep 40 minutes later, and we wouldn't even need to set an alarm. We would just wake up 8 hours later, and our bodies just knew this is the way our cycle should be running. Now, after the first month, the kids had to go back to school. So the rest of my family went back to Earth time, and I spent 2 more months working on Martian time. That was hard, because there you're working on shift for 4 days or 5 days, then you get back on time with your family, and you're basically it's like jet lag. You're trying to flip your clock back so you can actually spend time with your family, and then you flip your clock back the other way. And that's really hard. I think by the time we had done 100 sols, the whole operations team was pretty much done, right? That's about as far as you can do and still live life with the rest of the Earth. Ironically, I think if we were all on Mars, it'd be easy. We'd all just sync up and it'd just be a regular day.
Well, Elon Musk has got the right idea then. Let's all head off to Mars.
Yeah, that would be great.
I read in a book not too long ago about a study that was done about sleep cycles, human sleep cycles. And what they found was that the most natural, just based purely on our physiology, the most natural cycle was for humans to have, it was just over 24 hours in their day. It was probably right around 24 hours and 40 minutes. I mean, I want to say that was about what it was. They put people in, it was a dark room with no lights or something, and they just measured when do people naturally go to sleep and when do they naturally wake up, and they found that that natural cadence was just over 24 hours. So interesting. Maybe Mars knows something we don't.
Yeah, my experience was totally consistent with that. It's hard when you're trying to stay awake at 5 or 6 in the morning because there's no sunlight. But once the schedule has come all the way back around and the sun is out and you're synced up with that, we found it to be very straightforward and easy.
Yeah. Well, Curiosity landing on Mars was an incredible technical feat. Can you tell us about some of the technical challenges that needed to be overcome? I'm sure there were, hundreds, if not thousands of them, but maybe just pick a few of the most interesting or challenging that your team worked on.
Well, there are a tremendous number of challenges just to operating on another planet. The rover is operating many light minutes away from Earth, so we don't get telemetry in real time from it. It has to do what it does autonomously. The most difficult part of this is really at the end of a journey of hundreds of millions of miles, the spacecraft has to land itself on the surface of Mars through a process we call entry, descent, and landing. And in that process, which takes place over about 7 minutes, the spacecraft goes from 13,000 miles an hour in approach velocity to Mars to 0, so it can land safely on the surface. And in order to do that, it uses a heat shield, it uses a parachute, it uses a rocket pack, and it uses a device called a sky crane, which lowers it down to the surface of Mars safely and then flies away so it can get a nice, clean landing. And all of that has to happen completely autonomously. It has to happen perfectly, because if you miss any of those steps along the way, then you're not going to land on the surface. And it has to happen without any contact from Earth. So it's a very challenging sequence of events. We spend a lot of time testing and working on it and trying to simulate it as much as possible on Earth. But there are key challenges there.
How do you simulate it? I mean, given that the Earth's gravity is very different than Mars, how do you simulate that environment?
So we can't simulate the gravity. So really the first time the sky crane system that I'm talking about was used for the first time on the Curiosity rover. And it will shortly be used for the second time to land on Mars on the Perseverance rover this February. But the first time it's really run under real conditions, under real gravity and everything, is on Mars. That is the first time you can do it.
That's terrifying.
So you cannot test it end to end here on Earth.
Wow.
Now, we try and test as many of the pieces as we can. So we take the parachute and we simulate it in a wind tunnel. For Perseverance, they actually put some on a rocket and flew way up to 100,000 feet at Mach 3 and then released parachutes up there where the conditions of the Earth's atmosphere are similar to Martian atmosphere. You can't get the the gravity right, but you can get the atmosphere right. We have radars that are used to track the surface on Mars as we're coming down. We'd put those on fighter planes and use them to fly down these super steep trajectories to simulate the landing trajectory on Mars and check that the radar worked under those conditions. And then we'd run tons of simulations, Monte Carlo simulations, where we take all these different pieces that we have, we string them together, and we run them over and over and over again in simulation to try and find every possible failure mode and deal with as many of them as possible. But there are still things which can go wrong on the way down, which we know could be fatal to the mission. It's always a risky endeavor. You do the best you can to make it as robust as you can, and then you have to let the spacecraft go do it all by itself on landing day.
Wow, it's like sending your kids off to school, watching them get on the bus, right? It's hands off at that point. You can't do anything. You just have to trust that they know how to do it themselves. That's
right. And you got to go watch them do it. In fact, you can't even watch them in real time. It lands on Mars, and then 7 minutes later, we get the radio signals back on Earth that tell us whether it actually landed on Mars.
7 minutes. I was going to ask about that. So it takes about 7 minutes for the I guess radio transmissions to make their way from Mars to Earth.
Right. That's right.
That's quicker than I would have expected.
Well, it varies depending on the distance from Earth to Mars, because that varies over time depending on where we are in our orbit. So it can be short, it can be long, depending on where we are.
Okay. And you mentioned the sky crane. Once the sky crane drops off the rover, is its job done and it just, floats off into space?
It flies away using its rocket fuel, and it will run out of fuel and basically crash land on Mars about 200, 300 yards away from the main rover.
Okay. So there's a wreckage on Mars somewhere of the space crane.
Right, that's right. Still sitting there. You can see it from orbit, actually. We've taken pictures from orbit.
Oh, really?
We can see where the parachute ended up, and we can see where the sky crane ended up, and then we can actually see the rover itself going around on Mars.
You have just the coolest job. People probably never say that to you.
I am blessed to have this job. Trust me, I enjoy it. Yeah. Every day. There is nothing like being in the control room when the rover's on the surface and looking at pictures at 2 or 3 o'clock in the morning as they come down and thinking, we are the first human beings ever to have seen what we're looking at right now. And in 24 hours, these pictures will go out to the world and everybody else can see it. But right now, at this instant, it's just the 5, 6, 7 of us here in this control room. We're the first people ever to see this.
Again, that's magical. What an incredible experience. Huh. Well, you're the engineering manager for a mission called Psyche, Journey to a Metal World right now. What can you tell us about that project?
So this mission is going to visit a metal asteroid. So in the orbit between Mars and Jupiter lies the asteroid belt. And at the outer edge of the asteroid belt lies a unique body. It's an asteroid which is about 150 miles in diameter. So it's about the size of Massachusetts. And based on measurements from Earth, we believe it to be made up to 50%, maybe more, of metal. And that's a type of world that we've never visited in the solar system before. We've visited worlds made of rock and made of ice and made of gas. But a world made of metal, that's something that's unique. There are really not very many metal asteroids, and Psyche is by far the largest of them. And that we have questions about where it came from and why it's out there. And so our whole mission is to go out there and figure out how this body was created, what it looks like, and what its role was in the creation of the solar system.
I read that Psyche is about 200 kilometers in diameter, which is about 125 miles. To put that into perspective, I grew up on Hawaii, and turns out that is about 3 to 4 times the size of the island of Oahu in Hawaii. So that's a pretty big asteroid.
It's a big one, definitely. Yeah.
And I hear that it's worth quite a bit of money. Not that we'd ever be able to extract the cash from this asteroid, but if you were able to mine all of the metal, the ore in there, it would be worth many, many, many. I don't even remember what it was, but it was a huge number. Is that right?
The head of this mission, our principal investigator, Dr. Lindy Elkins-Tan, did sit down and calculate the amount of metal that's in that asteroid based on metal meteorites that we've seen. You can scale that up to the asteroid, and then you can calculate the theoretical value of all that metal. And I think it was $10,000 quadrillion, but it was a big number. But
some ridiculous number.
But it's not. If you ever did bring that back to Earth, you would crash the metal markets literally. So you could never get that money from it. And we can't bring the metal back right now. That technology is not technology that we have. We have the technology to visit it, and maybe in a future mission to bring back samples. But the technology to go that far out in the solar system and actually mine it is technology that we still need to develop.
Yeah. Well, speaking of Lindy Elkins-Tanton, who's the principal investigator, and interestingly enough is right here at ASU in my backyard, she said that the mission is so complicated that no one person can understand it, but it all has to work together perfectly for decades without fail. Now, if that's not a tall order, I don't know what is. What are some of the best practices or procedures that you and your team at NASA have developed over the years to mitigate risk?
We actually have a very rigorous risk management process that we run on this project, on the Psyche Project. It involves something called a 5x5 matrix and rating risks by their consequences and their likelihood and putting them on this red-green type of table and whatnot. But really, the most important part of the process is not so much what that table looks like or what the numbers are, but the fact that we meet on a monthly basis as a leadership team, and we spend hours every month discussing what the risks are on the project, how they're developing over time, and communicating the risk to each other. And that's a very, very important part of the process, and I think something JPL is very good at. Like I said, when we landed on Mars, for instance, we knew that there were some things which could kill the mission with a single failure, or if we had a super bad weather on that day or something like that. So, given that, the important thing is that we communicate those risks before we launch so that everybody involved understands what risk we're taking. And then if we see problems, people are not surprised and they go and they deal with it. This is, I think, one of the strongest features of NASA and JPL, that they understand risk and that they manage it well, and that they have that very forward-looking attitude once we're in flight. If we find a problem, it's not about recriminations. It's not about going back and trying to find who to blame, because all of that conversation has already been had as part of these risk conversations. We all know we're taking the risk together, and now we got a problem to solve, and we're going to solve it. And that's, key, I think, in order to really managing risk and making these missions successful.
Yeah, I love that. Thank you for sharing that. Let me jump back just a little bit to before Psyche started. The mission itself is, of course, incredibly complicated, fraught with risk, fraught with complications. But the process for pitching the idea to NASA sounded like it was in itself a formidable challenge and just a huge process. Can you spend just a couple of minutes telling us about what that process looked like to develop the pitch to do this project?
Yes. The Psyche mission is the 13th or 14th missions in NASA's Discovery Mission Program. And actually, we call it the Psyche Project because the Discovery Program, is made of multiple projects, which include the Lucy Project and the Dawn Project and a bunch of other projects which you may have heard of that go out and explore the solar system. In order to become a part of the Discovery Program, the head of the mission, the PI, needs to put together a mission proposal and propose that to a review board at NASA. And I think in the round that we proposed, there were 28 mission proposals that went into this process, and there are only 2 that came out the other end of the process. So the odds of getting selected there are low, and the effort that you need to put together a proposal which shows that you have a viable deep space mission is high. And it's a 2-year process. You go through 2 steps. You go through 1 round of competition. And in our case, we went from 28 entries to 5 in the first round, and then those 5 were given a few $1 million to go off and round out the design, and then they were down selected to 2 missions at the end. One is the Lucy mission, which is going to visit Trojan asteroids, and then our mission, the Psyche mission, which is going to visit a metal asteroid. That process, which takes place over that couple of years, is a fun one, but a challenging one, because you start with an idea from a scientist, right? And then you've got a blank sheet of paper to work with, and you've got to take that idea and turn it into a mission architecture and show that it's viable and can be done on a certain cost and a certain schedule by certain people with certain technologies in order to win that competition. And you have to show that you've got better science and better viability than the other projects. it's a unique process, and it's a wonderful process. I really enjoy it because you pull together a team of maybe 20 or 30 people, and you put that whole proposal together. It's a very small group compared to the hundreds of people that are working on Psyche now.
And the word proposal, and certainly the word I use before pitch, really doesn't do it justice. I mean, I think of a proposal, and I think of something we spend, 5 or 10 or 40 hours at the most putting together for a big project. Your team is spending years, and this is millions of dollars to put this proposal together, right?
Right, because the total value of the Psyche mission, when you include the launch vehicle and everything, is upwards of $900 million. That's the cost commitment we're asking NASA to make in order to fly this mission. And so, we spend $10 million just putting together the proposal for it because they want to know that it's viable. Nobody wants to commit that kind of money just to find out at the end, oh, I'm sorry, it doesn't actually work. So yeah, these are big pitches. The step 2 proposals are created over a period of about 9 months and end with a site visit where a review board of 30 or 40 people come and visit you and grill you over the course of 8 hours on your design in person. And that's in addition to the written proposal itself, which pushes 1,000 pages by the time you're done, and that you've turned in, that you've given to that review board so they can read it and understand it before they come and grill you about it.
Yeah.
It's a challenging process. It's really going through the forge, right? You're really being forged by fire. But I think it does actually make better missions because when you know, as you're putting together a proposal, that you're going to be challenged by a group of experts, you spend a lot of time making sure that you understand the engineering and that you put together a good proposal.
Sure. I imagine the criteria by which NASA selects the mission or the projects is based on some balance of risk versus reward. In your opinion, which I assume is the same as JPL's, but maybe you have your own nuance, I don't know. What's the best result that you can imagine for the Psyche project? What could the project potentially discover that would benefit NASA or mankind in general?
Well, our principal investigator has a theory on where Psyche came from. Because it's a mostly metal world, one of the theory that she's developed is that all planets have metal cores in them. The Earth has a big iron core inside of it. And one of the explanations for where Psyche came from is that it was once the inside of a planet that was forming, or planetesimal, a baby planet that was forming in the asteroid belt, and then that baby planet collided with other baby planets that broke it apart, and what's left here is the piece, or maybe a partially intact baby planetary core. If that's the case, then by going and studying Psyche, we can learn about not only where the solar system was created, but we can learn about our own Earth. We can study the core of our own Earth in a way that we can't do on the Earth itself, because to get to the Earth's core, you have to drill through hundreds, thousands of miles of rock. It's too hot. It's too hard to get there to actually visit the core. But maybe out here in space, we've got a sample of a planetary core that we can look at and actually understand our own planet from it. And I think just advancing the knowledge that we have of the solar system, of our own planet, of the universe would be a great outcome for this mission.
So the theory is that the composition of Psyche may be similar enough to the composition of our own Earth's core that the studies and results that you get from it would be applicable to the Earth.
Right, or to other planets, Venus,
and
Mars,
other planets.
Jupiter.
Got it.
It gives us a critical piece in our knowledge of understanding of how the solar system was created.
I see. Well, I'm going to jump off onto a tangent here for just a second. While working at NASA, you spent about 4 years from 2013 to 2017 as a lecturer and guest speaker. What was your message during that time, and how did you come to the conclusion that sharing this message was something you needed to do?
I've been blessed, I think, as part of the Mars program and getting to do a lot of outreach work where we get to talk about the work that NASA does. NASA's core mission, NASA is formed by the U.S. government. We work for the taxpayer. We're here to advance knowledge for the nation and ultimately for all of mankind. It's important that we share the knowledge that we get. And I think it's also important that we share and talk about the missions that we do, and that we use these missions to inspire the next generation of scientists and engineers, because these are inspiring missions. These are the types of things that we can get to encourage kids to study science and math and build things and just show what we can do with ingenuity and with innovation and the things that we can create. You know, I hope that out of the work we do, we inspire the next Steve Jobs, Elon Musk, and the next moon landing, the next missions, the things that advance the frontiers of knowledge and the frontiers of what we do in space.
Well, going back to the missions at NASA, can you talk a little bit about some of the tools that you use to break down a project as big as Psyche, so you can get organized and make progress towards, you know, your objectives as a large team? How do you organize all that information?
So the main discipline in which I work and continue to work, have worked and continue to work, is what we call systems engineering. And systems engineering is a discipline that's about taking all the different pieces of a spacecraft, the electrical, the mechanical, the aerodynamics in the case of entry, descent, and landing, as well as pulling in the scientists, pulling in the operations team, and making all of those pieces work together. You need multidisciplinary people who can see the big picture and can understand how all the pieces go together to pull these big, super complicated things together to make something like a spacecraft work. And systems engineering is one of these things that was really, I think it was invented in the U.S. in the 1950s and 60s as people were trying to build launch vehicles, and they were having trouble getting, you've seen videos, I'm sure, from the 50s or 60s of launch vehicles exploding when people tried to launch them. The disciplines that needed to be developed in order to manage all of the different pieces, when you have hundreds of thousands of pieces, all of which that have to work well simultaneously, you need these systems engineers who are looking over the whole system and making sure that everything will work together and that the risk is balanced across the system, and that ultimately, when time comes to launch, that the thing is going to work.
Yeah. Well, let's talk a little bit more about communication. In any profession, communication is really important to the success of the projects, and that's certainly the case with engineering as well. I find that the difficulty with which communication is achieved is correlated to some extent, anyway, with the size of the team. Now, you've had experience leading large teams of engineers and scientists. What are some of the granular strategies that you've used to do so? In a large team environment, how do you ensure that the right people are communicating with each other?
Well, that's partially art and partially science, I think. Within systems engineering, we have a rigorous system that we use. That's the science part, where you write requirements and you break down the system into individual requirements that can be tested and verified. And then you send those down to the subsystems that verify them, and then they send the data back up and you verify that the data is correct. And then you put it all together and you verify at a higher level that all of the requirements work together, and you verify those next level of requirements. And eventually you build up the whole ladder so that when you get to the end, you know that the whole spacecraft will work together. That's the basic idea. And there is a science to it, ways to write requirements, ways to break apart the system in ways that make sense so that you can test each piece separately. And as part of the design, you build in the ability to test the system. These systems are so complicated, you could build a system that literally can't be tested. And so part of what you do is at the beginning, you think, I've got this super complicated thing. I can test this piece over here. I can test the parachute here. I can test this computer separately, as long as I don't attach the computer to this other mechanical thing. You make all those decisions up front to try and break it, decompose the design into these pieces. Now, there's a part of this which is art too. I mean, when we were doing the Psyche proposal, we were working with a team at Space Systems Loral, now Maxar, which is located in Palo Alto. So they're located in San Francisco, the Silicon Valley area, whereas we're located in Pasadena and the LA area. We spent a lot of time getting on the plane, flying up there. They're flying down to us. I think over the course of 9 months, we had 26 face-to-face meetings, because there is a part of this which is you just got to get the people in the room and make sure that everybody is understanding and comprehends what's going on. Get on the whiteboard and draw things. and make sure that everybody understands their part, that the interfaces are clear, that the specifications are clear. There is a part of this which is just that human element. And I think that's one of the things I enjoy about systems engineering. It's part art and part science, and it's a combination of the technical and the human to make it all work together.
I'm curious, do you have an estimate of what percentage of your team's time is spent just communicating with each other versus doing the actual, development work?
Well, it varies by the level of people, right? And in the job that I have, which is managing the team, I spend 90% of the time doing communication. Now, there are people on the team who spend much more of their time, right? 50, 60, 70% of the time doing the work. And part of my job as the manager is to make sure that we communicate clearly enough that they can do the work and do it right without having to spend all their time communicating. So we really divide up the process like that.
Interesting. Well, you've worked with a lot of engineers over the years. What are some of the traits that you consistently see in the best engineers? What are the specific skills or talents that they have that make them great?
Well, first I'll say that, there's a diversity of skills and a diversity of answers to that, because there's so many different roles on the project that an engineer who's good at one thing will be good at one part of it, and an engineer who's good at another thing will be good at another part of it. So let me answer that question for systems engineers specifically, which is different than the electrical engineers, the mechanical engineers, or the folks building. The systems engineers have the ability to see the big picture and to drill down and deal with problems in detail. And most importantly, they have the judgment to understand when they need to drill down in a problem and when they can just let the problem go, because there are other people who will deal with it. Because if you it's what Lindy was saying, these systems are too complicated for any single person to understand all aspects of the system. So the good system engineers have the judgment to be able to understand which parts of the system they need to understand and which parts of the system they can leave to other people to understand, so that when it all comes together, it goes. That's a lot of good communication skills. It's a lot of good judgment, and it involves technical depth as well. So it's a lot of skills that come together to make a really good systems engineer.
Yeah, it sounds like that role requires much more than just the engineering education. It's almost a separate additional education on top of engineering.
Yes, and historically, a lot of what's happened is people get engineering education, and then they learn the communication parts of it, the soft skills, via experience. I mean, that's where a lot of that comes from. Now, that's changing now. Universities have started to create systems engineering programs. There are people who come out with system engineering degrees. But still, there's a bit of this which is art and experience, which is hard to get at the university level, because you don't see it in action until you're dealing with a group of, say, 100 people, right? Some of these things, these personal dynamics, they change as you go from 10 people to 30 people to 100 people to 500 people. So until you've been in a program that has 200, 300 people in it, you don't really understand what those dynamics look like and what you got to do.
It's just like testing for a Mars landing. You can only do so much, but there are aspects of it that you just can't test until you actually get to Mars.
That's right. So you build a pyramid of tests, right? A whole bunch of low-level tests, then some higher-level tests, then some higher-level tests, then the best testing you can do, and then you go to Mars and you do it. And so you are dependent on all the work done by all the members of the team. Yeah. And that's very important to be able to pull all those people together.
Well, we're getting close to being out of time, so I'm going to ask just a couple more questions, and then I'll let you go. What should we be looking forward to seeing from NASA over the next 20 years?
20 years. Wow. There's a lot of great missions that are out there potentially. Well, Psyche, of course. We'll fly that mission in a couple of years. We launch in 2022. Everybody should look for news of that. In August of 2022 is when our launch period opens. We have the Perseverance rover, which is going to be landing in February. We have a Mars sample return mission, which is in work now. And, hopefully we'll be actually taking samples that Perseverance rover collects and bringing them back to Earth so they can be examined by scientists. And of course, we have commercial crew, which is going. So we have new launch vehicles, American launch vehicles taking American astronauts into space. And eventually, the goal is to land astronauts back on the moon. I think we're trying to get to the first woman, and the next man on the surface of the moon will hopefully come out of NASA and the space program. So it's an exciting time for NASA. There's tons and tons of work going and tons of great missions out there.
What are some of the biggest challenges that you run into at work?
Well, that's a very interesting question. They're the technical challenges. Half of the spacecraft which are sent to Mars fail historically. So it's just a tough environment to operate in. And then there's just the communications challenges, right? Because you're pulling together these diverse people in all these different disciplines and all these different backgrounds. And you're trying to get people to work towards a common goal. And so there's all the challenges associated with that. The reason I hesitated at the beginning is because I admit that I kind of take these challenges for granted now. So I don't think of them, when you say challenges, it sounds negative, right? And this is the part that makes the job fun, these challenges. So they're challenges, but they're also the job, and they're the fun part of it. So
yeah, that's the puzzle that you get to put together, right?
Yeah, we get to solve some of the most complex engineering problems out there, and that's the fun of it. Yeah, lots of challenges.
Listening to you talk about communication, and so many of the guests on our show have talked about the importance of communication within engineering teams. It almost seems like engineering teams should bring on, I don't know, a social worker or a therapist or someone just to facilitate communication between people. That would be a really interesting experiment, I think, to see how much more efficient a team can operate if they had someone whose role was just dedicated to helping people communicate.
Well, we have people like that at JPL, actually. We
do.
When we are first putting missions together, when we're bringing these blank sheets of paper and we're bringing all the different disciplines into the room, we have an area of JPL called the Innovation Foundry that is dedicated to trying to take these ideas and turn them into things we can build. And within the Innovation Foundry, we have a team which we call the A-Team, which is a team for doing brainstorming and for doing rapid idea generation. And that team has trained facilitators in it. The facilitators aren't people who were facilitators by career. They are generally senior engineers who have then gotten facilitation training. I've gotten a little bit of that. We do like de Bono method, I think, is one of the methods that we use in our facilitation. And the job of those facilitators in that room is to get these diverse people, and over the course of just 4 or 5 hours, rapidly integrate the knowledge that they have and turn that into designs. And then after that, we have Team X, which takes them and turns them into technical designs, which are also facilitated jobs. But again, most of the people who do that are people who started as engineers or were trained as engineers and then picked up the facilitation training later. That's a very important part of the job, particularly when we're creating new missions from scratch.
That's fantastic. You mentioned was it de Bono method?
Yes, that's one of the management methods. There's a whole slew of different management methods out there,
okay,
and that's one of them. That's the one I happen to have gotten training in.
Interesting. I'll have to check that out. Well, last question for you here. I saw a picture of you and your family in the article. We talked about this earlier, where you guys were all on Mars time, and I'm making a little bit of an assumption here, but it seems like in addition to being a rocket scientist, you're also a family man. With all the demands placed on you owing to, the high level of importance role that you have at NASA, how do you balance your personal life with your professional life?
That's a great question, and it's a challenge for everybody. But I think it's very important to have that balance. I will go back to what I said about one of the important skills that system engineers have is the ability to know when to penetrate into a problem and when to let other people solve it. That kind of same judgment applies to your personal life versus your work life. You need to set boundaries and understand when problems need to be solved and when you need to spend time with your family and make all these things work. So I specifically dedicate time to the family over the weekends in particular. The other great thing about being part of NASA is that, unlike in some positions, what we do is public. I've taken my kids to the lab and shown them the things that we work on, the spacecraft that we build. They understand what I do and they understand the importance of what I do. And so I think when I'm off working on Mars time or third shift or whatever, right, they are part of the adventure that we do. And I think that's invaluable as well. So yeah, it's balance, but it's also integrating them and kind of making sure that they understand what the work life is, and they understand that I appreciate them, and that I'm going to show up at soccer games and school and do all of those things. And my wife, of course, is absolutely critical to making all that happen too, right? Just like building a spacecraft, managing a family is a team. Got to do it together.
Yeah, that's an interesting way to think about it. There really has to be kind of a manager in the family, right? Someone who is putting all those pieces together and making sure it works correctly. Well, David, thank you so much for spending this time today and sharing some of your experiences. It's been just fascinating, and I'm deeply grateful that you're willing to take some time and just share it today. So thank you so much for doing that. How can people get a hold of you?
You can find me on LinkedIn, or you can find me on Twitter. We do a lot of, actually Facebook also, we do a lot of social outreach. You can also look for on Twitter, at Mission to Psyche, I think is the Psyche Twitter handle. You can also go to the JPL website, jpl.nasa.gov. And you can find it. Search for the Psyche mission. Google the Psyche mission, and you'll find information about the Psyche mission as well. And on Twitter, you can follow me. I'm Mars Timer Dad, but it's spelled strangely. MarsTimrDad. So there's a story behind that, but we'll leave that story for another day.
Part 2. Okay. All right, David. Oh. I do have one more. My wife made me promise to ask, any sightings of little green men out there?
Not yet, no. If we find any, we'll be sure to let you know. Trust me, that would take care of our funding problems for a long time if we found little green men. Or women.
All right, David. Thank you so much.
Thank you very much. Thanks, Aaron. It's a pleasure to speak with you.
Hey, everyone. David asked me to include this quick correction to something he said during the interview. When the Curiosity rover landed on Mars in 2012, it actually took 14 minutes for the signal from the rover to reach the Earth, not 7 minutes. The 7-minute event he mentioned has its own significance, and you can read more about that in the show notes. I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please leave us a positive review. It really helps other people find the show. To learn how your engineering team can leverage our team's expertise in developing turnkey custom test fixtures, automated equipment, and product design, visit us at testfixturedesign.com. Thanks for listening.